Some of the harder questions for linear programming don't just give you the program, they give you set text which you need to extract the linear program from. So this process is called formulating a linear program. So we're going to have a look at that in this video. We've got 3 examples that we're going to consider. Okay, the first one, we've got a small wristwatch company. They make 2 types of wristwatch. We've got a standard version and a deluxe version. The standard version takes a machine 20 minutes to assemble. The deluxe version takes the machine 30 minutes to assemble, and there are 10 machine hours available per day. Only one wristwatch can be assembled at any time. So there's some kind of constraint in this text by the machine, essentially. Each wristwatch made uses exactly 1 glass front, and the standard version and the deluxe version use the same glass, 25 glass fronts available per day. Okay. On top of that constraint, we also have the wristwatches require specialist components. So we've got component A and component B. The table below shows how many of each specialist component each wristwatch needs in order to be assembled. So the standard wristwatch needs 4 component A's and 2 component B's. The deluxe one needs 1 component A and 9 component B's, but we have 82 A's and 144 B's available per day. Okay. And then finally, the information here, a standard wristwatch sells for £30 each and a deluxe one sells for £50. The company wishes to maximise the income from the sales of the wristwatches. Okay, so onto the question, part I, defining your decision variables clearly. Okay, if the question says that, we must make sure we define them clearly. Okay, it's easy to overlook. We're going to formulate the above information as a linear programming problem. Okay, so the first thing to notice is the objective, which is given at the end of the text. And I know this is the objective because it states what the company wishes to do. And we can see that it wishes to maximise the income. Okay, slightly different to maximising profit because we are ignoring the costs of the cost of production. It's just looking at maximising the income. So the objective is going to be to maximise the income, which I'm going to call I. And I need some variables. I don't know what to put here yet. So the 2 variables that we're going to have is how many standard wristwatches the company is going to produce and how many deluxe wristwatches the company is going to produce in any given day. So let's define our variables. So I'm going to say let X be the number of standard wristwatches produced in a day. Okay. And then similarly, I'm going to let Y be the number of deluxe wristwatches produced in a day. Okay. If you can try and squeeze them all onto one line, then the decimal marks will obviously line up with the words above. Okay. So defining our 2 variables, X and Y, and it's going to be standard and deluxe wristwatches. Okay. But the important thing when you're defining variables is you should use the phrase be the number of. Okay, that should be present. Can't just say let X equal the standard wristwatches. It's got to be the number of standard of wristwatches, and it says produced in a day, because everything here is all about being how many are being produced in a single day. Okay, so just be clear when you're defining your variables. So X and Y. Okay, so now that we've got these defined, we can now state our objective function. So a standard wristwatch sells for £30 each. So if we sell one, then the income's going to be 30. If we sell 2, it's going to be 60. If we sell 3, it's going to be 90. In general, if we sell X or make X and sell them, then the income will be 30X. So that's the income from the sales of standard wristwatches. Similarly, we're going to get plus 50Y because if Y is 1, then we're going to get £50 income. If Y is 2, we're going to get 100. If Y is 3, we're going to get 150 and so on. And in general, the income from the deluxe wristwatches are going to be 50 times the number of deluxe wristwatches sold. So that's 50Y. So that's the income from the standard wristwatches. That's the income from the deluxe wristwatches. So that's the income altogether, and that's what we want to maximize. Okay. Okay, the constraints. Okay, now the constraints are above the text here, above the table. So we've got this here. This gives us a constraint. And what you'll tend to see in an examination setting is the constraints will be given as a paragraph or a line assigned to each constraint. So in this case, it takes 20 minutes to make a standard wristwatch and 30 minutes to make a deluxe wristwatch. So if I make 3 wristwatches, standard ones, it's going to take an hour. If I make 6, it's going to take 2 hours. In general, it's going to take 20x minutes to make all the standard wristwatches, plus 30y minutes to make all the deluxe wristwatches. So this is the time to make all the standard ones. This is the time to make all the deluxe ones. Combine them together. That's the total time that I require. That cannot exceed 10 hours. But because these are in minutes, I need to convert the hours to minutes, so that's 600. We could have written the whole thing as an inequality in hours, which is fine. So x over 3 plus y over 2 must be less than or equal to 10. That's the same inequality. So either is fine. Okay, I'm going to stick with 20x plus 30y is less than or equal to 600. And in fact, we could simplify that as well, because 10 goes into all of those. So you could end up with 2x plus 3y is less than or equal to 60. Again, that's a completely equivalent inequality. So any of these are absolutely fine. Okay, but I'm going to stick with the red one. Okay. All right. Each wristwatch makes exactly 1 glass front. I've only got 25 glass fronts available, so therefore I cannot make more than 25 watches in a day. So x plus y, so the number of standard plus the number of deluxe, that's the total number of wristwatches, that cannot exceed 25. And then I have 2 more constraints here as well, constrained by how many of component A I have available and how many of component B I have available. So this top one here, let's call it the component A constraint. 4x plus y must be less than or equal to 82. So 4x is the number of component A's that I need for the standard wristwatch, and y is how many component A's I need for the deluxe wristwatch. So that's the total number of component A's I need. That cannot exceed 82 because I only have 82 available. And this line here will produce yet another constraint, which is going to be 2x plus 9y must be less than or equal to 144 for the same reason. Okay. So put all that together. I've got 1, 2, 3, 4 constraints plus my objective function. So here we go. 1, 2, 3, 4 constraints plus my objective function. I've also added in my 2 constraints that x and y cannot be negative, since x and y both represent the number of watches to be made. Okay, so that gives us this. I've solved the linear program already. Well, I haven't solved it. I've graphed all the constraints already, because this video is not about solving a linear program. It's about extracting the program from the text. All right. Okay. Part 2 of the question then does ask me to solve the linear program. It says clearly state the number of each type of watch that should be made and the total income this produces. So linear programming, the optimal solution will lie on one of these 6 vertices. I can actually ignore O, you don't have to include O. So solving all these simultaneously, you can get the points for A, B, C, D, and E. A is the point 0, 16. B is the point 6, 14. C is the point 15, 10. D is the point, say 18.7, I think it was. Just checking with the equations here. 18.7. And then E was the point, which line was that? this one, I think, yeah, 10.50. Okay, so those are the 5 coordinates, or you could include the origin as well for completion, but it's not going to be that because the income at 0, 0 is 0. Okay, I'm going to run all of those points through the objective function, which is up here. So 30x plus 50y, so 50 times 16, that is 800. The income is going to be £800 there for that one. 6x plus 14y, so that's going to be 30 times 6 plus 50 times 14 is 880. The next one is 30 times 15 plus 50 times 10 is 950. And the next one is 30 times 18 plus 50 times 7 is 890. And then finally we've got 10.5 times 30, which is 315. And we'll look at that one in a bit more detail in the next video, because there was an issue with that point for this problem. But fortunately, that is not the one that we are interested in. This is the one that we are interested in, because that is the one that produces the highest income. Okay, so the answer to the linear program is the maximum income value is £950. Okay, and if you did simplify that to 3x plus 5y, you have to convert to make sure the money is 950. And that occurs when you make 15 standard watches. Wrist watches. And 10 deluxe wristwatches. Okay. And if it is a contextual question, okay, in this case, wristwatches to context, then you should state your answer in context as well. Okay. All right, that's the first one. I'm going to go through the other two a little bit quicker, now that we've got a general idea. All right, so the second. We've got a drama department at a school. They're looking to cast students for production, and they choose to cast for both the lower school and the upper school. At this time, we have our decision variables defined for us, okay, L and U. The 5 leading roles must be taken by upper school students, and there's a chorus or extras group of 15 students, which must consist of only lower school students. Apart from the 5 leading roles in the chorus, there are a further 12 named roles that must be assigned, but they can be lower or upper school, and the drama department can cope with a maximum of 45 students in the production altogether. The drama department find working with upper school students easier than lower school students, therefore they decide to maximise this function here. It's just a function they've made up. Okay, so write the above information as a linear programming problem. All right, so again, we can see that we've got the objective at the bottom. It's not always the case, but in these 2 questions it has been. So we're going to maximise. Not got a letter with it. It's not income, it's not profit. We could just leave it alone. You could just maximise L plus 2U. You don't have to put a letter to it. You can just maximise an expression. Subject 2. And now we're going to use these constraints. So the 5 leading roles must be taken by upper school students. So for that, we must have the number of upper school students being at least 5. There is to be a chorus extras group of at least 15 students. Of 15 students, consisting only of lower school students. That means we must have at least 15 lower school students taking part in this production to make sure that that's cast. Apart from the 5 leading roles and the 15 students in the chorus, we've got a further 12 named roles that must be assigned to students, but they could be lower or upper school. So altogether we've got 5 plus 15 is 20, plus 12 is 32. So we've got 32 kind of parts to this production. They all must be filled. So the number of students taking part must be at least 32. Okay. And then finally, the drama compartment can cope with a maximum of 45 students in the production altogether. So therefore, the total number of students must be less than or equal to 45. Okay. So those are the 4 constraints, and there's our objective expression there. All right. So that's the answer to part I. All right, write the above information as a linear programming problem. Part 2, find the optimal solution to this linear programming problem. Well, again, I've taken the liberty of doing up the program already. I'm only going to check the points B and C because B is clearly going to be bigger than A and C is clearly going to be bigger than D, so I don't actually need to check those. But if this were an actual question in an exam, you should check all vertices of the feasible region. So B, that has coordinates. Well, it's the intersect of L is 15 and x plus y is 45. So if L plus U is 45. So if L is 15, then that means U must be 30. And C is this one down here. So we want U to be 5, which means L must be 40. Okay. So it's going to be one of those 2 points because we're maximising L plus U. And then the expression L plus 2U, not got a letter for it this time, so I can't put P as my column header, but it doesn't matter. Right, L plus 2U, so it's going to be 15 plus 60 is 75, and then 40 plus 10 is 50. So we're maximising that, so that's going to be this one. Therefore, you should cast 15 lower school students and 30 upper school students. Okay. In this case, the objective function doesn't actually mean anything physical. It's just a preference function or preference expression. So that's the solution to the linear program. And then finally, in reality, the optimal solution for this linear program might not be the best choice for the production. It's just a reason why this might be the case. Why might this not be the best? Well, you might have some lower school students who are good at drama, so you might want to cast them in some of the named roles. It might be easy to work here at A. You might not have enough auditions to fulfill all 45 slots. There's lots of different reasons that you can give. Just one of them for 1 mark is good enough. Okay. It's got to think a little bit laterally about the context that the question is written in. Okay. Right, and one final question is all about cupcakes. So a cake company has been asked to bake 2 types of cake for a village fete. Let C be the number of chocolate cakes made for the fete, and let V be the number of vanilla cakes made for the fete. The fete organisers have requested that there must be at least 200 cupcakes altogether. There must not be more vanilla cupcakes than chocolate cupcakes, and there must not be more than 3 chocolate cupcakes for every vanilla cupcake. The cost to make a batch of 10 vanilla cupcakes is £2, and the cost to make a batch of 10 chocolate cupcakes is £3. The company wishes to minimise the total cost of making the cupcakes such that the organisers' requests are met. Okay, so this is going to be a minimisation problem because the company wishes to minimise. So the objective is to minimise the cost. Now, C is the number of chocolate cakes made for the fete, but it costs £3 to make 10. So actually, I'm going to minimise the cost, which is going to be 0.3C plus 0.2V. Okay. Now you could put 3C and 2V, you would get the same answer, but your final cost C value wouldn't actually represent the cost of the problem. So just be careful with the numbers. Occasionally they can throw this out, this type of thing. The batch of 10 cupcakes is £2, but V is the number of vanilla cupcakes made at the fete. So each cupcake costs 20p, not £2. Okay, so just make sure you've got your wits about you when you're looking at wordy questions like this. Okay, then we've got 3 constraints which are nicely bullet pointed this time for us. So there must be at least 200 cupcakes altogether. Nice and easy. We've only got 2 types, so we know that this first constraint is just going to be the number of chocolate cupcakes plus the number of vanilla cupcakes must be at least 200. I cannot exceed that. So it cannot be less than that. The second constraint. Now, these 2 constraints take a little bit more thinking, so just be really careful. And if you need to, just plug in some numbers. There must not be more vanilla cupcakes than chocolate cupcakes. Okay, there's another way of saying this, is the number of chocolate cupcakes must be greater than or equal to the number of vanilla cupcakes. So chocolate cupcakes must be greater than or equal to the number of vanilla cupcakes. Right? There must not be more vanilla cupcakes than chocolate cupcakes. So if I make 5 vanilla cupcakes, I have to make at least 5 chocolate cupcakes. If I make 20 chocolate cupcakes, then I cannot make more than 20 vanilla cupcakes. Okay, so if you need to throw in some numbers, then do. And I recommend just writing an inequality down and then just checking that this inequality satisfies the sentence when you've got some numbers in there. All right, because it's so easy to make a mistake. Particularly with this third one. There must not be more than 3 chocolate cupcakes for every vanilla cupcake. Now, it's not as simple as a straight relationship. Okay, we're going to have a constant kicking around. But where does that constant go? Then must not be more than 3 chocolate cupcakes for every vanilla cupcake. 3 chocolate cupcakes for every vanilla cupcake. Oops. So the number of chocolate cupcakes must be less than or equal to, okay, cannot exceed, 3 times the number of vanilla cupcakes. So if I make 5 vanilla cupcakes, I cannot make more than 15 chocolate cupcakes. And the bit that throws students most here is I've got the word 3 chocolate cupcakes, but yet 3 is the coefficient of vanilla, not of chocolate. And that's because it's inverted the other way, just by the way the maths is extracted from the text. So just throwing in numbers will really help with these, I promise you. So ignoring that for a minute, there must not be more than 3 chocolate cupcakes for every vanilla cupcake. If I'm making 1 vanilla cupcake, I cannot make more than 3 chocolates. If I'm making 2 vanilla cupcakes, I cannot make more than 6 chocolates. If I'm making 3 vanilla cakes, I cannot make more than 9 chocolates, and so on. In general, if I'm making V vanilla cupcakes, I cannot make more than 3V chocolate cupcakes. So therefore, C, the number of chocolate cupcakes, must be less than or equal to 3 times the number of vanilla. Okay. Those are the hardest types of inequality to pull out from text. A lot of students will make the mistake of 3C is less than or equal to V. Okay, so just be really careful. All right, but those are the only constraints in this problem. Okay, so we've got this one and these two, and then we've got our objective. So again, just like the other 2 examples, I've already done it because I'm not interested in solving the program in this video. I'm interested in extracting the program. So this is an infinite feasible region. It's got 2 vertices, A and B. A has coordinates 100, 100, and B has coordinates 150, 50. Okay. And we want to minimize the cost. Okay. So let's calculate the value of C for each of these points. So 0.3 times 100 plus 0.2 times 100, that's going to cost £50. And 0.3 times 150 plus 0.2 times 50, that's going to cost £55. So the minimum is this one. Okay. So therefore, the solution to the problem is to make 100 chocolate cupcakes and make 100 vanilla cupcakes too. And all of that is a total cost of £50. Okay. All right. That finishes this video. I don't want to do anything else other than mention very briefly from the question that notice that these are cooked in batches of 10, and 200s are obviously multiples of 10. So I'm making 10 batches of chocolate and 10 batches of vanilla, so there's no issues. But in the next video, we're going to have a look at integer programming, where that might have been an issue. Okay, so it's just an interesting point to note on that. All right. If you have any questions, please just pop them in the comments below. Thank you very much for watching this formulating a linear programming video.